Okay, today we are going to be discussing the Monty Hall programming problem. Now, the Monty Hall problem says we have three doors in front of us, one of which has money or some other prize, and two of which have nothing. Our job is going to be to guess which one, of course, has the prize behind it. So the way it works is we are going to pick one of these doors. Let's say we pick this one, number 2. Then the host, this would typically happen on a game show, the host would look at the other two doors. He knows which ones the money is behind, and he's going to eliminate the door that we did not pick and that has nothing behind it. We are then given the option to switch our choice or stick with what we had originally. When you look at this, you'll say, well, it's a 50-50 shot. It's either going to be here or it's going to be here. So it doesn't matter if I switch or not, so I could not. But it's actually always in your favor to switch, and it's because of this information that the host gives you. So when you start off and choosing a door at random, you have a 1 in 3 chance of getting the door. I mean, the money could be here, here, here. You pick one of them randomly, it's 1 out of 3. But once you eliminate one of them, you all of a sudden have more information than just your 1/3 chance. So to use an example, let's say the money is in door number 1, and we could either pick door number 1 and pick it the right time, we could pick door number 2 and pick it wrong, or we could pick door number 3 and be wrong. So if we picked door number 1, if he eliminates door number 2, we should stay. If he eliminates door number 3, we should stay. But if we picked either door 2 or door 3, we should switch. So we actually have a 66 or 2/3% chance of winning if we switch, because the chance of picking it right on the first time is only 1/3. And this is easier to see once we add more doors, but we'll do that in a minute. So that's the theory behind it. You should always switch your door because you have such a low 1/3 chance of picking the right door the first time. So today we're going to write a computer program to see if our theory is correct. So I'm going to switch over here to my program. There we go. So the first thing I'm going to do is import a module called random, and I'm using the Python programming language. And I just typed import module, import random. So random is a module that allows us to do a lot of things with random variables, and we are going to be using these, of course, to figure out where the money is placed, and in our simulations which door our person would pick. So I'm going to go ahead and print out 3 doors, never switching. So for our first simulation, we're just going to imagine that we never switch. We pick one of the doors, don't care which one the host eliminates, we're sticking with our original option. So we're going to have a variable, I'm going to call it 1, you can call it something like number 1. It's going to keep track of how many times, or out of how many simulations we successfully get the prize. Then I'm going to create an array. I'm going to call it list of doors like this. I like to use camel case. We're going to set this to have the elements 1, 2, and 3. So now we're going to make a for loop for our simulations. I'm going to choose to first only do 10 simulations. I'm going to set the random variable money to be a random.choice. This means take the module random and call the method choice. And the method choice takes in a list and outputs a random element from that list. So I'm going to pass in my list of doors, door 1, door 2, or door 3, and it's going to store one of these values in money. And I'm going to do the same thing with my choice. So we're saying pick a random door for the money to be behind and pick a random door for a person to pick. Okay. So if we're not switching, we want to check if our choice was equal to where the money ended up. Because if it didn't, then because we didn't switch, we can't get it. So if this is true, I'm going to add 1 to our total, and I'm going to go ahead and print out U1. And then outside of our for loop, after we've run through 10 simulations, I'm going to say U1, then comma 1 times. So inside this print statement, I'm printing out this string, then my variable, and then another string. And this, using commas like this, we'll go ahead and put a space here and here. So let's go ahead and run this. Let me switch this. Here's our output. We won only 2 times. So in theory, if we don't switch, we should win 33% of the time, because we have a 1 in 3rd chance of picking the right door. So now this was a small sample size, so let's go ahead and bump it up to, let's do 1,000. And save. And it'll take a second, print out a bunch of times, and you see we won 311 times, 31.1%. So that's closer to our theoretical 33%. And then if we go ahead and bump it up even more, I'm going to go ahead and take out this print statement because it can cause the program to lag a bit because it has to print out all these times that we won. Go ahead and run it again, save, and now 32.72% of the time. So pretty close to our theoretical 33%. But now we have to check what happens if we switch all the time, right? That's supposed to be the better strategy. That's supposed to get us a win 66% of the time. Okay. So there are a couple of ways to do this. One way, you can write a bunch of if statements saying if I picked door 1 and the money is behind door 3, that means he'll eliminate door 2 and then I'll switch to door 3. But if you think about it, I'm going to go ahead and switch back to just me. We have 2 options. We could either pick the one with the money initially, or we could pick one other. If we pick the one with the money initially, he will eliminate one of these 2, and then we will switch to the other one and be wrong. If we don't pick the money one initially, say we pick door 2, then he will eliminate, the host will eliminate the other door and we will switch to the money every time. So if we pick the money initially and always switch, we will always be wrong. If we don't pick the money initially and always switch, we will be right. So this makes our program actually a lot easier. We don't have to write out all those if statements to cover every single case. So I'm going to go ahead and copy these first few lines. I'm going to change this to say always switching. We reset our number out for much we've won. We keep our list of doors the same. I'm going to go back down to say 100 iterations. Going to take the same, putting the money in our choice. But now, remember, if we didn't pick the right door to start and then always switch, we will always end up with the right door at the end. So we can go ahead and say, if our choice was initially wrong, then we will win once we switch, and we don't even have to simulate that anyhow. We could add a print statement that says like switch and you won. But it doesn't matter which door we picked or which door the money was behind. If we're always switching, we are always going to win if our initial thing was wrong. And then if money did equal choice, we would then switch to the other door which didn't have our money in it, and we would be wrong. Okay. I'm going to go ahead and put my print statement outside of my for loop. Do the same thing you won number of times. Okay, save. Go ahead and run this. Switch to our output. Down here you'll see the first time again, the first one was still on 10,000 runs, and we won 33% of the time. This time on 100 runs while always switching, we only won 54% of the time, which is not close, We'll go ahead and run it again, 62% of the time. I'll go ahead and bump up this second one to 10,000 simulations. Run it again, and there we have our 66% chance. So again, if you never switch from your initial choice, you only have a 1 in 3 of getting the money. But if you always switch, then this or this will work. This or this initial choice, because then you'll switch to the money. Another way of thinking of this, so that was only with 3 doors, but what if we bumped it up to 10? So I'm going to go ahead and draw 1, 2, 3, 4, 5, 10 doors. And I'll go ahead and put the money in number 10. So now you can see I have a 1 in 10 chance of guessing this initially. But what if after I guessed, let's say I guess this one, the host goes through and eliminates all of these doors. Now again, it's technically a 50-50 shot on whether the money's in here or here, but initially I only had a 10% chance of guessing it right. With that added information that it's between these two, I now have a much higher chance of it being in the one I didn't pick. In fact, I think it's 90% for 10 doors of it being here. So again, you should always switch. And we can put our theory to the test in the practicalities of the computer by going back to our, there we go, back to our program. And this time we're going to try it again, but with 3 doors. So I'm going to head and copy my 3-door never switching. Going to rename it to 10 doors never switching. And go ahead and add a couple of doors to here. I'm not going to list the fancy for loop thing you can do in here. This just looks cleaner. Okay, and then I'm going to copy my always switching code. Change it again to 10, and change it, add in 10 doors. Go ahead and save and run this. Switch to our output. So with 3 doors and never switching, we won 1/3 of the time. 3 doors always switching, we won 2/3 of the time. 10 doors never switching, again, we're only going to have a 10% chance of guessing the right door. And if we did 10 doors always switching, we have a 90% chance, all because of that information the host gives you by eliminating every door except for your choice and the money. So that is how to do the Monty Hall problem using Python programming.